Alright, this will be our final video then. Thanks for sticking that with me this long. Alright, angular momentum is always conserved, just like its linear cousin. This means that if there are no external torques, just like there are no external forces in momentum, exerted on a rotating object, the angular momentum of that system stays constant. So we essentially figure out that the initial angular momentum Li must be equal to the final Lf. So that means that the initial I, or a moment of inertia, times the omega I must be equal to IF omega F. This implies that the change in momentum of inertia will cause a change in the angular speed of the spinning object, that the total amount of angular momentum stays constant. You can see this exact situation happen in a lot of things, but as figure skaters are probably one of the best examples of this. A figure skater who sets into a spin with her arms and legs spread out from her axis of rotation has a high moment of inertia. That I is big. Since there are no external torques in her, the angular momentum has to stay constant. As she spins slowly, she pulls her arms and legs inwards towards the axis of rotation, decreasing her moment of inertia. Oh, I just messed that up, didn't I? Which will result in an increase of her angular speed. And if you look up here, that's why we have I, initial I, and final I, because unlike masses, you can alter your moment of inertia just by kind of moving around a bit differently. Then number 5, if there is an external torque on the system, then that torque will change the angular momentum of that object. So as far as the formula goes, before we kind of had a impulse momentum theorem, and this is going to probably look similar to that. So we have sigma tau, and that's going to be equal to the change of momentum over the change of time. And by doing that, we get sigma that's equal to I omega F minus I omega I all over delta T, which we can alter to this delta omega over delta T, which is I alpha. And if you recall, that's kind of translating back to our angular net force equation. In addition, we could also branch off from here and multiply delta T onto their side and get sigma tau delta T equals I omega F minus I omega I, which is the angular version of the moment of impulse momentum theorem. We get the same equation as the equation in 8.53, which refers to the books. All right. Our final, I know we're finally there. Our final unit to kind of make into a rotational thing is kinetic energy. Now, we don't have to worry about the potentials because they don't really care much about spinning, but kinetic does. So rotational kinetic energy is a measure of the rotational energy the object has. Since kinetic energy has to be moving, spinning energy counts as moving. The formula for our rotational kinetic energy, we're going to use K rot, or rot, for rotational energy. And then as a reminder, we have omega as the angular speed. And our equation looks like K rotational equals 1/2 I omega squared, which, once again, if we translate back into linear, we just have k equals 1/2 mv squared. That is our kinetic energy equation, just shifted to an angular form. This means that there are two types of kinetic energy. We have translational or linear, and that's going to be when we move the center of mass of an object, and also rotational kinetic energy, just spinning the object. If a sphere, a cylinder, and a hoop start at rest on the exact top of a ramp and are released all at the same time, which one reaches the bottom first? This one's kind of looking at the moment of inertia equations, because they have a big influence on how much the objects will rotate. So the explanation here, the sphere will be first. And it will be first because it has the least amount of moment of inertia. If you look at the equations back here, two-fifths mr squared, I mean, if we translate that to decimals, that's 0.4. Cylinder is 0.5 mr squared. So it has a bit more moment of inertia than the sphere. And then finally, the hoop is just mr squared. This one has the most moment of inertia. So we can clearly say, too, that the sphere is going to be first, and that's going to be followed by the cylinder. And then our third place finisher will be the hoop. However, because it has more angular momentum, it'll also be the one that rolls the furthest, which is kind of an interesting thing. I'd love to show you that if I have access to our stuff at school. To wrap things up, our conservation of energy formula look like this. And when we write this out for this specific example, we're starting off with potential gravitational energy. So this turns into, I'm sorry, that shouldn't be there, NGY initial, where Y is the height. We have no initial kinetic, no work other, no final potential. But because of the fact we have mixed kinetic energies now, we're going to have some translational kinetic energy as well as some rotational kinetic energy, where this I is dictated by the shape of the object. Okay, so the last thing that we need to worry about is, well, the last thing that's included in your notes is just this very back page, which includes all of the equations in a little bit more of an accessible format. And I've been saying before how these things, we have a translational and an angular version now. So as far as these things go for our velocity, our kinematics materials, we can just translate our kinematics equations back into their angular forms. So we have omega equals omega naught plus alpha t, and omega will be in radians per second. Our x value is just going to be the theta, and that'll be equal to theta naught in this equation, plus omega naught t plus 1/2 alpha t squared, and that'll give you radians as it's solved currently. Our next one, this guy, that'll translate into omega squared equals omega naught squared plus 2 alpha theta versus theta naught. Notice these equations are the exact same as their translational counterparts. It's just we're replacing them with their angular variables. So over here, v, that translates to omega, and then we have delta theta over delta t, and that'll give us rads per second. Sigma f equals ma translates to sigma tau, so torque, equals your I alpha, and that'll be Newton meters, or you can also write that in kilograms meters squared per second squared. K equals 1/2 mv squared, that'll be k rot equals 1/2 I omega squared, and that'll be giving you joules still. Work equals FD, it'll still be work. Let me draw that a little differently so you can actually see it's a W. And that'll be work rotational, and that'll be equal to tau theta, and that'll still give joules. P, we get two equations for this. We get L equals I omega, and we also get L equals mass times VR, depending on which form of your equation is more easy to use. And then finally, sigma f equals delta p over delta t. That translates to sigma tau equals delta L over delta T. And that'll give us newtons per meter, or kilograms meters squared over second squared. All right. And then we have this little table here. Position, linear symbol is x. It's measured in meters. Angular symbol is theta, measured in radians. Remember the relationship, as always, is the translational version equals the r times the angular version. Speed is v, or velocity, meters per second. Our angular version is omega, and that's rads per second. And to translate, v equals r omega meters per second. And then acceleration is a, meters per second. Linear is alpha. We have rads per second squared. And a equals r alpha. And we get meters per second squared. All right. Our final thing here, it just gives you the three types of accelerations and what they actually wind up doing to an object. So if we're having centripetal acceleration for the very first part of our unit, the object will not have a constant speed, a constant linear speed, nor will it have a constant acceleration linear, because it's constantly changing its angle. However, this does maintain a constant tangential speed, and it has a consistent acceleration while we're looking for which way is it accelerating towards the center. Tangential acceleration, a constant speed is no, because it will be speeding up or slowing down. It will have a constant acceleration in a straight line. It will not have a constant acceleration while it's turning. And this will be a yes. And then finally, an angular acceleration will have no constant linear speed, no constant straight line speed, no constant tangential velocity, or angular velocity, but it will maintain a constant angular acceleration. So I'm hoping that works out. If you guys have any questions, feel free to ask. And then from here, you should start to look at the practice problem video. So thanks for sticking out with me. I know this was a long one. So have a great day.